Okay, so I think I will start. Good evening, everyone, or maybe some of you are good afternoon or even good morning. I'm very excited to open this interesting session on flash floods in arid lands. I must say that in most of the works dealing with this topic, including the talks tonight, there is one issue that everyone are writing about and keep mentioning, and this is the problem of scarce data and large knowledge gap about flash floods in desert environment. And yet this evening, we will hear 5 very different lectures dealing with different aspects of flash floods in arid regions. And our first speakers, I would like to invite Professor Aaron Yair from the Hebrew University of Jerusalem. Aaron, you can share your screen and we will see your presentation.
Aaron, you have to open the microphone.
שלום.
יוסף, אתה רוצה שנעבור לדובר הבא בינתיים?
הנה הוא מתחיל, בסדר.
אוקיי.
אני יכול להתחיל? אוקיי, רואים את הכותרת?
כן, תתחיל.
אוקיי. The title of my presentation is Clay Dispersion, an important factor in channel runoff generation in a semi-arid, less covered area. אני מקבל הודעה DDD conference requesting remote control of your scene. Okay. Introduction. Do you hear me?
Yes, we can hear you. You can start.
Special relationships or connectivity represent a basic concern in our understanding of geomorphic processes and their effects on the structure and function of ecosystems. High values of connectivity are indicative of an efficient system for the transfer of water and sediments through the drainage system, while a low hydrological activity encourages infiltration losses, sediment deposition, and spatial variability in the redistribution of water sources. Many factors may affect the degree of connectivity, and the importance of a given factor may vary in a wide range of conditions. I am going to tell a story in a semi-arid area in Israel. You see the red line here. Average annual rainfall in this area is 280 millimeters, and the material is less was deposited during the upper part of the Pleistocene during under wet conditions. This area is characterized by very strange features. Piping, you can see it very developed in the area. Bank collapse in many places and so on. But what is important thing is that many channels disappear in the downstream direction. You see here, here, and in many other places. So we have a lot of discontinuities in the system. Although in some places the valleys are very wide, but when you go downstream, the valley becomes very, very narrow, and then it disappears. And the question, why is it that we have such features, quite unusual? Regarding the hydrological characteristics, we have something very special. A very high frequency of flash floods in ephemeral streams in the less covered land area.
Aaron, I'm sorry to interrupt you, but we cannot hear you very well. Can you please maybe be closer to the microphone?
Okay.
Thank you.
Is it better now?
Yes, thanks.
So we have a very high frequency of flash floods in ephemeral streams in a less covered dry land area. 4 to 8 flows events every year. In fact, this is the place where we have the highest number of flash floods in Israel. But we have also two very special characteristics. Very low peak discharges, even at extreme rain events. In addition, runoff generation occurs at very low rain intensities, 5 millimeters per hour, far below the final infiltration rates reported in the literature for the less covered areas in this area, 10 to 15 millimeters per hour. So obviously we have many questions to answer. Okay. Now the hypothesis for what I've said is the following. The hypothesis is that when the runoff generation is limited to the channel area.
Aaron, try to speak a bit louder. I'm very sorry, but people write me that they cannot hear you.
Okay. The hypothesis advanced.
Thanks.
Runoff generation is limited to the channel area. This hypothesis is based on the following findings: on hill slope properties, toposequence. I will explain it later. Rainfall properties, hydrograph characteristics, and data from sprinkling experiment, and particle size distribution and clay mineralogy of the alluvial fill. What we can see here is the rainfall in the area for 2 consecutive years. In fact, what the characteristics of these 2 years, that we have very low rain intensities. In fact, 84 to 85% of the rain is with intensity below 5 millimeters per hour. So very, very low rain intensities. And also the question, if 85% of the rain is below 5 millimeters per hour, how can we explain a high frequency of channel flows in the area? Now, in addition to the low rain intensity, we have very often intermittent rain showers. Also, we need to take into account the fact that limited rain splash effect due to vegetation cover, mainly of annuals. So, in fact, we need to explain how come that we can get a high frequency of channel flow with very low rain intensities. This is an example of a storm. In this case, we have a storm with a high rain intensity. You can see it here, above 40 millimeters per hour. Look at the graph. In fact, we have a very steep rising and falling leaves. Such a feature is generally characteristics of saturated areas when the runoff starts and then immediately stops when rainfall stops. But also we have here, in fact, small flow with a very low intensity here. This is one case. In fact, in this case, runoff coefficient at peak flow was 0.005% of the rain received by the drainage area. I forgot to say that the drainage area is 11 square kilometers. So what characterizes the flow here? Very steep rising and falling limbs, usually indicative of saturated areas at the vicinity of the monitoring station. Let's take another case, completely different. In this case, rainfall lasted for many hours, but still, if we look at the discharge here, very low discharges, 0.2 cubic meter per second. Rainfall was continuous, flow was continuous, but with very low discharge. In this case, the storm rain amount was 59.4 millimeters, very high. This storm was preceded by a storm of 36 millimeters a week ago. Runoff coefficient at peak discharge was 0.0032% of the rain received by the basin at peak flow. In this case, with the continuous rain, we would have expected a significant contribution from the adjoining hill slopes. This did not happen. In addition, runoff generation at very low intensities, below 5 millimeters per hour, is far below the values of final filtration rates reported for less soils, usually 10 to 15 millimeters per hour. And we do get runoff with an intensity below 5 millimeters per hour. Very low runoff coefficients at peak rain intensity. So how can we explain this? Now, what is interesting is that in areas, the basin where we've been working covers 11 square kilometers. If we look at the infiltration curve during the Holocene, and even before, in the dry area of Israel, Dead Sea, and the area lower, we can see that for the drainage basin with 100 square kilometers, we would expect very high peak discharges. Also, almost 1,000 meters cubed per second. And what we do get is very, very low. So we need to explain this strange behavior of the hydrological behavior of the area. So we have adopted three different ways. First assumption was that there is no runoff contribution from the hill slopes. And therefore, what we've decided is to look at soil properties along the hill slopes. The hill slope, 400 meters long. We had 8 boreholes, 1 in the channel itself, and then 7 along the slope, 400 meters. And we looked at the properties of this along the slope. Now we can look at the chemical data. We can see very clearly that along most of the slope there is no change. The highest values are always top of the slope, sodium, chlor, SO4, and BC. And in fact, the high figures here are due to a very special sedimentary unit, which has nothing to do with soil properties. In fact, what we do see here is we have no change in soil properties along the slope. In fact, what we do get here, we don't get here the classic toposequence effect. According to the toposequence ratio, we would expect a change in soil properties from the top of the slope to the base of the slope. Nothing happens here. The reason is that in most rains with low rain intensity, there is no runoff. And if there's no runoff, we would expect a change in soil properties along the slope. The other thing, if you look at the clay content, again, we can see number 1 is the top of the slope, 8 is the channel. We can see that the highest values in clay content are in fact at the top of the alluvial channel, of the alluvium in the channel. And this is very important. I'll come back to it later. Now, if you look at soil property, at the soil moisture content along the slope, again, practically no change along the slope. Also here, this point here is the channel. So if we start from here to here, no change. Here is again the top of the slope where we have a different sedimentary unit. Now, also something very important, the issue of infiltration into the channel itself. The green light is the channel, all the others are the hill slope. We can see that along the hill slope, there's no change in the soil moisture. For the channel, we have deep infiltration down to 20 centimeters, and then it drops very quickly. This is one event, and this is the whole year, the same feature. In addition, we have looked at the mineralogical composition of the clay fraction. We took one sample at the top of the alluvial channel from 0 to 10 centimeters, according to the data given to us by Dr. Sandler from the Geological Institute. Smectite and delete are the predominant clays in the area. Smectite, as we know, is a very important clay because it absorbs a lot of water, certainly in a dry area. So we decided to conduct a sprinkling experiment in the channel itself in order to get some information on the issue of infiltration, runoff, rainfall, runoff infiltration in the channel itself. You can see how it looks the channel itself. The experiments were conducted in August, the highest time of the year. The first run in blue with an intensity of almost 12 millimeters per hour. It's summertime, so it took some time for the clay to absorb the water. Runoff started after 20 minutes, and practically it remains the same until 50 minutes after. 1 hour after, we have conducted the second sprinkling experiment with a higher rain intensity, 29 millimeters per hour. The surface was wet, and in fact runoff started within 3 minutes up to 50 cubic meters per minute. Remained simply the same, and here we stopped. So when the surface of the top of the alluvial material is wet, in fact we can get runoff with any rain after that. And the reason for that is that we do have, I'll come to this later. Now if we look at the stratigraphy and characteristics of the top of the alluvium. We can see the behavior 2 units. The upper one, coarse grained, a lot of voids and relatively good connectivity between the voids. The porosity of this one is approximately 17%. If we go to the bottom, to the lower layer, we don't have many.
One more minute, please. Or דקה. You have one more minute if you want to continue.
No problem, I wait for you.
Aaron, you can continue with the lecture.
What we can see here,
You have one minute left.
1 minute left. Okay. I'll skip this one. Conclusions. Data presented fully support the hypothesis that the chances for runoff generation are significantly higher over the alluvial deposit than over the adjoining hill slopes. The mechanism of clay dispersion easily explains the very high frequency of storm rain events in the study area. In case of clay dispersion, in case that clay dispersion is achieved at the end of the first rain event, the chances for runoff generation are much greater than the pooling rain events. The limitation of this process to the alluvial channel also explains the very low peak flows even in extreme rain events, as well as the steep rising and falling limbs of the hydrographs. Data presented conform with the concept of partial arid dissolution observed in humid areas. However, the similarity ends here. Whereas in humid areas, this pattern is associated with saturated areas. In the present study, the pattern is associated with the structure and composition of the alluvial field. Finally, more attention should be devoted to the clay dispersion process of runoff generation in dryland areas where smectite is the most dominant clay. Thank you very much.
Thank you very much, Professor Aaron Yair. We are short in time, so I would like to invite our next speaker, Eran Khalfi. Eran is finishing his PhD studies at the Geoflume lab at Beni Gurion University of the Negev, and he is joining the Desert Flash Floods Research Center. Eran?
Okay, hello everyone, shalom lekulam. If you can't hear me well, please tell me and I will speak closer to the microphone. I'm currently a hydrologist in the Dead Sea and Arava Science Center. However, this presentation is part of my PhD work, which dealt with the characterization of bedload discharge and both in unsteady flows in the thermal channel. It was conducted in Ben Gurion University of the Negev in the Unit of Environmental Engineering. And it's a joint effort which comes to compare Flume experiments that are conducted in Austin, Texas, together with the field experiments, which will be the focus of this presentation. So a little background, sediment transport is important for a variety of scientific, environmental and engineering aspects. For example, erosion of pillars and other structures which are constructed on riverbeds such as bridges or dams, erosion of riverbanks with settlements and alluvial farming. A recent example for that was just recently on March 2020 in Israel, in the Arava River, where there was big flash floods in the Arava River, and as a result, 40-meter widths of riverbank collapsed with all the alluvial farming. So what the gap this research comes to fill is that with a few exceptions of a Flume experiment, which are conducted in laboratory, very little is known or published about the hydrodynamic and bedrock transport in such extreme event as flash floods. The unpredictable nature of these events, together with many logistics and safety issues, can explain some of these gaps. And this study, together with novel equipment and very well planned deployment, enabled us to be on site in all these extreme events and monitor them. And we focused on two durations of the flash floods where the flow properties are most rapidly changing. The first is when a flash flood bore arrive over a dry riverbed. It's the first bore of the flash flood. And the second duration is later on in the flood, where another bore arrives on a column of moving water. So during those two durations, we monitored the flow properties and the bedload transport. So the main objectives are to better understand and quantify bedload transport in unsteady flow in an ephemeral channel. And the two main questions are, what are the flow properties in unsteady flows, and how does the bedload respond to these flow properties? The research is conducted in Nahal Eshtamoa. It originates in the Hebron Mountains and drained into the Be'er Sheva River. It has a drainage basin of 112 square kilometers with 5 to 6 flow events per year. The river alternates between bars and flats, with the nearest D50 flats to the station of 17 millimeter and the nearest D50 of the bar to the station of 98 millimeter. So this is an upstream view of the Eshtamoa gauging station. Actually, it's not quite a representative picture because it's right after some few very rainy days. In 90% of the year, the river actually looks like this. It is very dry without the vegetation. However, let's return to the instrumentation. So there are 30 sensors in the station for monitoring the flow properties and bedload transport. All are connected to a single data logger, which is very important for synchronization, especially when dealing with high temporal resolution, such as the bore duration. I will go over them briefly. For measuring the flow properties, there are 11 pressure transducers, which are located inside steering wells along the right and left bank. And they measure the variation of water depth and water slope which arrives to the station, which can affect the shear stress, which acts on the bed. We have two video cameras, one filming upstream, you can see the picture from this, and one filming downstream, you see these two holes over here, to the section where the bed load is monitored. And together with this target and an LSPIV software, we can conduct and calculate a two-dimensional velocity field of the flow. In addition, on this holder, there is a three-dimensional ECM, electromagnetic current meter, which measures the velocities of the flow in 3 dimensions in a frequency in 40 Hertz for characterization of the turbulence. Additionally, downstream to this picture, there is a conductivity meter, a turbidity meter, and an SVR, a surface velocity radar, for measuring the average velocity of the water surface. Let's turn to the bed load. So for measuring the bed load, there are 3 slot samplers that you can see over here. For measuring directly the bed load, the stones roll and fall into the slots and are measured. And we have indirect samplers. We have a pipe hydrophone, we have a plate geophone, and one which combine both, a plate and a pipe hydrophone. And recently, we deployed another plate microphone over here. All of these are indirect samplers, which measure the impact of the stone which hit these plates. Here on the river banks, there is a seismograph buried in the about half a meter inside the bank, and it measures the vibrations in the ground, which are generated by the rolling stones in the river. So all of this instrumentation are operated automatically by one of three sensors, which are located over here about 170 meters upstream to the station, except two, the three-dimensional electromagnetic current meter and the portable SVR, which are handled manually, which means we have to be on site before the bore arrives, and this requires very detailed planning. So this planning enabled us to be on site and to measure all the event in the last 4 years, all the flash flood events. And this is an example of one of the first ones. So this is filmed from the camera which is looking downstream. And I'm standing here in the middle of the river, waiting to measure three-dimensional velocity of the flash flood. And here in the circle is the research assistant waiting to measure with the SVR, the surface velocity radar. So I will play. And eventually the flood came. It felt more like a football team because there was so much noise of the bedload rolling on the ground, and this lots of flotsam which comes to you. I won't show the end of the video, but anyhow, if I'm speaking now, everything went well in the end, and I got out. The instrument, by the way, did not get out of the current meter. However, after this event and from this experience, we decided to put a permanent holder cemented instead of a human holder. So let's quickly turn to the results, some results from the experiments. So these are water slope. This is a figure of the water slope from all the pressure transducers arriving to the gauging station, which is over here, in three different durations of the flood. In red during bore arrival, in green during maximum flow depth, and in purple during recession. All the slopes refer to the 150-meter ridge immediately upstream to the station, and in brown in the Dalvik. So as we can see from the figure, the slopes during bore arrival is twice as much the magnitude of the slopes at maximum flow depth and recession. And this has an effect on the shear stress acting on the bed and may generate bed load transport during the bore. Another important hydraulic parameter when dealing with bed load transport is the vertical velocities, because they may generate lift forces. So this figure is vertical velocities measured by the ECM. Time zero is time of bore arrival. And we can see higher magnitude of vertical velocities during the bore arrival. And after the passage of the bore, about 30 seconds, there is a significant decrease. This result will not consistent throughout all of the bores, but we do see it sometimes. On the other hand, this result were quite consistent in all the bores. It's the turbulent kinetic energy, which is also measured by the ECM and is calculated by this formula, which uses all of the components of the velocities, all the dimensions. And what we can see here in blue is the wave. This is water depths rising from 0 to 20 centimeters. And the yellow are the average turbulent kinetic energy. So as you can see, in the beginning of the bore, there is higher turbulent kinetic energy and then a considerable decrease. And if we add now the bed load, which was measured from the plate microphone in pulses per second, we can see how this bed load responds to the imposed turbulence with higher bed load transport at the beginning of the bore, and then afterward it is seized when the TKE is also seized over here. I would like to show another example because this example consists of the two durations which I mentioned of the introduction, which are a bore which arrives on a dry riverbed, which is bore number 1. This is a hydrograph over here of the event. And bore 2, 3, and 4 are both which came later on in the event on the running river. So here we see the bore in blue, rising from 0 to 8 centimeters, the first bore, and this is bed load in red. So as we can see, as the bore arrives, we get some bed load transport, and after 4 minutes, it is completely seized, although water depths here are higher than here. This is bore number 1. And if we turn to bore number 3, again, we see that this is the bore rising from 10 centimeter to 25 centimeter. And again, prior to the arrival of the bore, there is no bedload sampling, bedload transport, 0. During the first minute of the bore's arrival, there is, we get some bedload transport, and after it passes, it's again completely ceased. So this clearly indicates that there are other forces than shear stress which generate this bedload transport, like we showed before, the turbulent kinetic energy. And this is bore number 4 of this event. And again, this bore raised from 25 centimeter to 45 centimeter. And again, prior to the bore, no bedload transport. And when the bore arrived, we do get some bedload transport and then a decrease. And when the bore reached the maximum flow depth, here the threshold for bedload at 10 million in Nehushtan is reached, and we start getting a lot of continuous bedload. This is what I was talking about, the comparison to the Flume experiments, which came to examine similar aspects. So this is a side view of the Flume, and I will show it in slow motion, the arrival of the bore. And we can see the turbulence over here, the high turbulence in the beginning with the Flume. And then we can see the bedload transport by sliding or rolling. There is not enough shear stress for saltating. And then bedload is ceased, although water depth here is much higher and the river is supposed to be stronger. So again, this is in agreement with what we saw in the field. Another achievement of the study was the calibration of the plate microphone with a direct slot sampler by deploying a novel mass aggregation method, which we developed. Just in brief, I'll explain the method. It means that accumulated mass is incremented only when there is additional mass which is equal to the sensitivity of the sensor, which means stones continue to fall into the slot sampler, but until it doesn't reach this threshold, we don't take data. So instead of taking data by constant time interval, we're taking the data by constant mass interval, and by this we reduce the noise when the fluxes are low and there is a sensitivity below the sensitivity of the sensor, and we avoid masking of high flux data. So here we can see the events that you saw in the video. It was a big event rising to 80 centimeter. And by using the mass aggregation method, we can see here the plate microphone, and in green, the slot sampler. Quite good agreement, and here is another event showing the same. And just one final slide is something that we're currently working on. I was showing you in the instrumental slide that there is a seismograph buried in the ground. So this is we are now working on calibrating the seismograph. And we're doing it with a research group from Potsdam, Germany, a seismic research group. And this is just an example to show. The upper figure is from Nehushtan. We have in blue the variation in water depth, and in red are the bedload transport by the plate microphone. And the down figure on the same timeline, we have the seismic signal. And we see that we have quite a good agreement with high signals with high bedload, and then a decrease as the signal decreases. I think that's it for now. Thank you for your attention.
Thank you very much, Eran. And we will firstly move to our next speaker, Dr. Rachel Armoza-Zvuluni from the Desert Flood Research Center.
Just a second. Can you see that?
Not yet.
Sorry. Okay.
Yes, now, yeah, we are seeing it.
Okay, so hello everyone. My name is Rachel Armoza Zvuluni, and I'm a researcher at the Desert Flood Research Center of the Dead Sea and Arava Science Center. And today I want to present a study examining sediment yields in the hyper-arid areas of the Middle East, exemplified by Nehushtan, Nahal Nehushtan in the Arava. Sorry. So in the hyper-arid environments of the southern Negev desert, high-intensity rain events generate flash floods with a frequency of about 1.5 floods a year. The geological and geomorphological characteristics of the drainage basins, they are affecting the peak discharge and the runoff coefficients of the flood events, of the flood. While the flow duration and the peak discharge determines the capacity and the characteristics of the sediment that are transported by the floods. Sediment characteristics are also affected by different characteristics such as soil types, land use, vegetation cover, and also by the interval between flood events. So with regard to the transported sediment, sediment particles move either as bed load, as Eran showed, near and in contact with the surface, or as suspended materials, as you can see here in the pictures, in the two pictures. Sediment yields can be evaluated by indirect approaches such as radioactive isotopes and remote sensing, and also by direct approaches. And that are based on the mode of the particle transport and the position. The suspended sediment that move in trajectories can be sampled and analyzed by sampling, by manual sampling and automatic sampling. Bed load that move in near and in contact with the surface can be monitored by also sampling, but also different sensors, as Eran showed. And we can also determine sediment yields by looking at reservoir deposition, and that's what we did. As we can see in the figure here illustrated on the right, sediment yield depends on climate and geological features. And in semi-arid areas, sediment yield is higher than in more humid locations. So we don't have a linear behavior with respect to the precipitation. The higher sediment yield in these semi-arid and arid environments is results from insufficient cover of the vegetation, unstable soils, and high-intensity rain events. Although this figure determine the sediment yield in a very arid climate, such as hyper-arid environments, it's not actually based on data that is taken from these locations. And data from hyper-arid environments is very limited because it's very hard to access these locations. The floods are very rare, and there's a lot of difference and variability in space and in time. And I want to present our study site. We studied the Nehushtan basin, which is located in the Timna Valley in the southern Arava. The Timna Valley is drained by two main wadi, the Timna Valley in the northern part and the Nehushtan in its southern area. This whole area is characterized by high temperatures and very low rainfall of only 25 millimeters a year. Here we can see the drainage area of Wadi Nehushtan. You can see in the orange arrow that the exit of the valley to the Arava was formerly open, but since 1958, this path was closed by a dam that was built as part of the infrastructure associated with the Tibna copper mines. So they actually wanted to protect the mines from flooding, and they built a huge dam that since 1985, it prevents runoff and transported sediment from arriving the Arava, and it's all collected in the reservoir area. Here we can see in a closer look at the reservoir after 2015 flood event, which is now flooded. And we can see the close proximity between the reservoir area, which is on the top, and the artificial lake, which is used for different activities in the park, touristic activities. And you can see here also the proximity to different touristic such as tents and cabins that tourists used to stay there, and a restaurant in the area. So the place of like where the river or the valley flows, it's located very, very close to human activity, and it's become a very big problem. Since the reservoir is filling up with sediment, and the level of the flood, the water is rising, the risk for human activity or for humans in the area and for infrastructure is rising. And this was like one of the reasons we started this research in the reservoir. So the main goals of the research were to study the sedimentary sequence of the deposited during the past 60 years in the Nehushtan reservoir. We wanted to calculate the overall and event sediment yields, and to compare these values with scant information that are available from sediment yields from hyper-arid watersheds in the Middle East. So the way we went about it, we characterized stratigraphic sections of 17 pits that were excavated throughout the entire reservoir to the depth of the former riverbed. As you can see here in the picture, we analyzed different event layers. The difference between them were recognized between using mostly the clay surface at the deepest pits, and at the shallow pits we recognized the differences between the layers by the gravel and the different sand matrices. You can see on the top right, one of the researchers that's standing inside one of these pits and taking pictures to analyze later on in the lab the different sections. So we dug these pits until we reached the former alluvial bed, and on the right and the bottom, you can see that in a white arrow, we found an artificial layer that was not part of the local material. And this was actually material was placed by the park maintenance people and when they tried to make use of this area after a long period, which were not they had no flood events, and they thought, okay, why don't we use this huge area located right under our noses? So this was used as chronological remarks in this work. As I said, we reached the former alluvial bed and we created a GIS layer, a raster that identify or exemplify the topography that was in the reservoir during like 60 years previous to this work. And in addition, we analyzed the current topography. This is, you can see on the right side, and you can see with in the numbers the different pits that were dug in three cross sections parallel to the dam. Comparing these two GIS raster layers actually gave us the total amount of sediment that was deposited in the reservoir in the last 60 years. The two former bigger flood events that were occurred in 2010 and 2015, we were able to create a GIS raster layers and identify exactly the layers or the volume of sediment in these layers. And with regard to other flood events, and I will move forward, as you can see here in the bottom on the right side, we found like in our two deepest pits that were pit number 2 and pit number 1.5, we found a record for 13 flood events, and this is actually the floods that were big enough to bring sediment to the reservoir. And by correlating these two pits, we determined the sediment load of each flood event, with compared to the thickness and height of the layer and the total pit depth. You can see in the main figure here the different cross sections, the stratigraphic sections of the pits. What we can say that the topography was remained very similar to the one that was there like 60 years ago, with the northern eastern side was the deepest, and the direction of the water, the flow, it remained the same. It was what made us easier for us to calculate and to analyze these data. Okay, so this is the sequence of the 13 flood events that were occurred during the last 60 years. On average, it's a flood event every 4.5 years, which is seem very, very small in frequency. But when we're looking at the intensity or the sediment yield of each event, we try to characterize three size groups. We found 5 very small flood events, which contributed between 25 and 48 ton per kilometer, per square kilometer. 7.
Please.
Excuse me?
One more minute.
1 more minute. Okay, so I'll move forward. So we found that actually the medium-sized flood events contributed the highest amount of sediment to the reservoir. And now moving to the overall analysis, we can see here that as we expected, the annual sediment load of the monitored hyper-arid basins is positively correlated with the drainage basin area. However, we also expected to find a correlation between sediment yield and drainage basin area. This is because it's assumed that the sediment yield is reduced with the increase of drainage area. However, we didn't find this correlation in this the basin we looked at, and the ones that are known from the literature. Nehushtan, the one we studied, is characterized by very low sediment yield amounts. And what we did thought to look at is to look at the flood frequency and to check whether this is a good predictor for sediment yield. And so when piling up the information from the literature and our information, we found that there is a positive correlation between the flood frequency and the sediment yield, and this may be a good predictor for sediment yield for different arid, hyper-arid areas. And I just want to go back to local perspective and to say that although we had a very large flood event in last March, which was, and its flooding area was very similar to the one we characterized in 2015. And although the rain was amount was very much smaller, and the reservoir water input was smaller, and what it's actually saying that the reservoir filled up with sediment and the water level rising up. This work was actually gave the municipality and the drainage authority enough tools to plan a better drainage or a better reservoir for the future of Timna, and the scientific data was actually evaluated by a lot of money that was saved for this purpose. That's it. I'll finish with that, and thank you for listening.
Thank you very much. We are running out of time and we will not have time for questions. So our next speaker is Rami Zaitouni, who is also about to finish his PhD at the University of Haifa. Rami, please. To share my my movie with you, because I already record my my talk. Let's see if it works. Hi everyone. So I am pre-recording my talk for this evening because I don't want to exceed the 15 minutes. I heard Convener is really strict about it. So today I will present our work on extracting flash floods with remote sensing tools in order to monitor the distribution and frequencies of the flash floods in arid regions. Remote sensing is a very powerful tool in order to extract data on floods. And we see a lot of recent work all over the world that uses remote sensing on this topic. The very high spatial and temporal coverage of remote sensing really helps a lot in order to extract the highly valuable data on floods and flash floods. However, in arid regions, we don't see as much researches, and we have two limitations of flash floods in arid regions that that make it harder for us to monitor the flash floods. The first one is the short duration of flash floods in arid environment. It usually lasts between a few hours to few days. And the second one is the color of the turbidity water that is not like the color of floods water in other places in the world. So we need to develop special methods in order to monitor flash floods in arid regions. And we can divide the studies that were already done on flash floods in arid environment using remote sensing by two categories. The first one is studies that uses satellite images of the flash floods in order to map and predict where the flash floods will distribute, where we have flash floods. And the second category is the studies that uses post-satellite image, post-floods satellite images, that those studies are trying to assess to measure the damage of the floods and the ecological impact. What we are trying to do is neither of those categories. We are trying to monitor the flash floods itself, not predicting where it will be and not measuring the impact of the floods, but monitor where the floods occurs. And we cannot do it by real-time monitoring from satellite images, because in order to capture exactly the flash floods, why it occurred, as I said, flash floods in arid environment are very short duration, and with the sensor that we have today, we cannot do it with good enough spatial resolution that can detect the smaller bodies that we have. What we do have that monitor in real time is ground data. We use hydrometric stations that are distributed in several valleys in the southern part of Israel. And those hydrometric stations measure the floods occurrence and some different parameters of the amplitude of the floods. But the main limitation is that each hydrometric station is measuring only in one very specific spot in the valley, and therefore we are missing the spatial data. Also, those hydrometric stations are very high with logistic effort, and this is one of the reasons that we are trying to develop some more easy to maintain methods. So the remote sensing data that we are using is mainly Landsat 8 images and Sentinel-2 images. We chose those two satellites because they have the shortwave infrared band that is very sensitive to soil moisture. And as I said before, we cannot capture the flash floods itself in real time, but what we are trying to do is capture the remains of the flash floods, which we see in the soil moisture the few days after the flash floods occurred with those images. And when looking at spectral signature that we are taking out of different images of those satellites, we can see that the spectral signature of dry valley pixels here in the yellow line, and the post-flood valley pixels. And doing was captured exactly during the flood. We also took this spectral signature. We checked different spectral indices in order to distinguish between dry and wet or dry and moist pixels. And we chose eventually two indices to work with. One is the NDWI, that takes the difference between the green band and the near infrared band, and the other one is the LSWI, which takes the difference between the shortwave infrared and the near infrared region. So what we see is that we can, if we capture the floods in time lag of 2 days, we can still see the signal of the water. But after the 2 days, we cannot. The pixel will look as dry valley pixels. The same is with the NDWI index, but notice that with the NDWI we have a problem that wet valley pixels are in between dry pixel of the valley banks and dry pixel of the valley. So that means that we will have to have two thresholds in order to distinguish those pixels that we are interested in order to detect the flash floods. We are using those graphs to set the threshold of dry and wet valley pixels, and then we can produce those maps of flow. And with those maps, you can see very clearly that the amplitude of the flood that is expressed here as the discharge, the maximum discharge, really impact our index values and impact our ability to see those floods, because here we have floods that occurs only less than a day. We capture the image less than a day after the floods, but it was with really low discharge, so we can hardly see the flow. And here we have a flood that we captured 2 days after it, but with a really extremely high discharge for this valley, and we can see it really clear. So we did a comparison between those two indices in order to understand how those two parameters, we have two parameters that influence our index value. One is the time lag between the end of the floods and the image capturing, the satellite image capturing. And the other parameter is the discharge. So in those graphs, we can see in the y-axis, this is the index value, and in the x-axis, this is the time lag in days. And the size of the dots here represent the max discharge. And we can see quite clearly that with LSWI, there is a lot of influence of the discharge on the index values, and we can see also the 2 days threshold that from 2 days we are not always be able to see the signal of the floods. But when looking at the NDWI, it's look like this index is indifferent to the discharge amplitude. And to conclude, I want to show you the Wadi Paran area that has two hydrometric stations. One is here and one is here. We can gain a lot of data from those hydrometric stations, but we cannot gain the spatial data of the area of different streams and channels. We will not know if there was floods in those places. but taking the shortwave infrared, this image was taken before the floods, and this image is taken less than a day after the floods, and we can very clearly see the absorption in the shortwave infrared that exactly where the water flow. And also, of course, in stream that we don't have hydrometric station in them. So with doing a combination with image processing, we can use this to produce the flow maps and know exactly where the flash floods occurred. So just to finish up, I just want to say why we are trying to use also the NDWI and not only the LSWI, which has better results, because we want to use other sensors that have a higher temporal resolution. For example, the planet CubeSat and the Venus satellite, but those satellites doesn't have shortwave infrared bands. So this is why we are trying to develop also the monitoring flash floods without the shortwave infrared, in order not to miss any floods because of the 2 days restriction that we found out that we have with the shortwave infrared. So thank you very much, and I will be now on live for your questions. Thank you. Okay, so we just finished the session on exactly the last second. We can still stay in this room because then the next session will start at 8 o'clock. So if you have questions for each of the speaker, you can, I don't know, maybe raise your hands and we will answer. If you want to leave the room, it's also okay, because actually the time is up, but we can still stay here for a few minutes. Okay, I see the question of Joel or Yoel about how long approximately does it take for VadiPixel to appear dry after the floods. So this was actually one of the questions that we asked ourselves before starting this project. And what we are seeing now is that the answer is 2 days. 2 days that after the 2 days, the spectral signature is being similar to dry pixels. Maybe with other spectral region like the microwave, we can enlarge it. We will check that, but now with what we checked, it's 2 days.
Okay, so does that then imply that the ground is not dry yet? It just looks dry, or is the ground already dry at that time because of evaporation, or how does that affect that?
So when we are looking with RGB images, also half a day after the flash floods, the soil looks dry. But with the shortwave infrared and also the NDWI, which is surprising because it's not supposed to be sensitive to soil moisture, but also with the NDWI, we can detect the signal of the water 2 days after the floods. Does anyone wants to ask any other speaker? Okay, so thank you very much, all of you that came to listen and all the speakers. And we will meet in the next DDD conference, maybe face to face and not screen to screen. So thank you very much.